Scientific notation. Learning goal. I can change numbers written in standard form to scientific notation. Before we dig into scientific notation, we're going to recap a little bit of the things we should already know just to make sure we're all on the right page. When multiplying a number by 10, the digits move one position to the left in the place value chart. So just to refresh our memory, we're working with just familiar terminology here, millions, billions, thousands, etc. So supposing we had a number like 3,425. If we put that into a place value chart, we know that that means there are 3,000s, 400s, 2 10s, and 5 1s. Now suppose we wanted to multiply that number by 10. It's fairly simple to see that each number then becomes worth 10 times more. And if we have 3,000s and we multiply that by 10, it becomes 3 10,000s or 30,000. So that gets moved over to the 10,000s column. So we move it one place to the left. Similarly, the 4 follows along. Now 400s becomes 4,000s when it's multiplied by 10. 2 10s becomes 200s. 5 1s become 5 10s. And since there were no tenths over here, we have 0 1s. So no shock that 3,425 times 10 is equal to 34,250. Now let's just look at that again without doing the place value chart. Supposing we've got 3,425 and it has a decimal here at the end. And theoretically there are zeros after that, but we don't need to worry too much about them. We want to be conscious of the fact that we've got this decimal here. So when we multiply by 10, what we're really telling it to do is move the decimal one place to the right. So the decimal is now there, and in order to move the decimal there, we have to put in an extra 0. If there are decimals in the number that we're multiplying, the same thing is going to happen. So supposing we had a number like 3421.68, and we're going to multiply that times 10, the same thing happens. We just have to take this decimal and move it one place to the right. So 3,421.68 times 10 is 34,216.8. Multiplying a number by 10 that's raised to a positive power is the same as multiplying by 10 multiple times. So in this example, 4 times 10 to the third is equal to 4 times 10 times 10 times 10. The 3 is telling us that we're going to multiply it by 10 3 times, which of course is the same as saying 4 times 1,000, because 10 to the third is 1,000, or 10 times 10 times 10 is 1,000. So the answer then is 4,000. Similarly, if you divide by 10, the decimal moves to the left, as each digit now has 1/10 of the value. So if we use an example here, and we divide that by 10, what we're saying then is we're going to take the decimal, and this time, instead of moving it this way to the right, like we were doing when we multiplied by 10, we're going to take it and we're going to move it to the left. So 247.689. Sometimes when dividing by a multiple of 10, you also need to add zeros on the left-hand side. Just as we did previously, we added zeros to the right-hand side when we're multiplying by 10. Here, we can start adding them to the left. So let's see what happens. We have a fairly small number here, 4.25, and we're dividing it by 10 to the third, which means we're dividing by 1,000. So we're going to take our 4.25, and we're going to move the decimal place 3 positions. So we're going to do 1, 2, 3. Put the decimal there, and we'll fill in the extras with zeros. And usually we put a 0 in front of the decimal place as well. So 4.25 divided by 10 to the third, or divided by 1,000, is 0.00425. In an earlier lesson, we found out that any number to the exponent 0 has a value of 1. So 10 to the exponent 0 is equal to 1. Similarly, 5 to the exponent 0 would also be equal to 1. Now, what happens if a number has a negative exponent? A negative exponent is the same as saying 1 divided by the number. Let's look at an example then. We've got 2 to the exponent -1. So that's the same as saying 1 over 2, or 1 over 2 to the exponent 1. That also means if we've got 10 to the -1, that's the same as 1 over 10. If the exponent is a negative other than 1, the exponent value stays the same and you divide by the power. For example, so here we've got an exponent of -2 on the 10. That means 1 over 10 squared. So you can see that the 2 here stays with the 10. So we've got 10 squared, but then the negative is what tells us to put it as a 1 over. Let's look at another example. 10 to the -6th. The negative tells us we're going to have a 1 over, and then we've got 10 to the 6th. So we keep the exponent 6, and we simply put it as a 1 over, and that gives us our 10 to the -6 is equal to 1 over 10 to the 6th. Let's look at another example now. We've got 3 times 10 to the -2. What does that turn into? Well, we can expand that out a little bit to say it's 3 times 1 over 10 squared. Knowing our rules for multiplication with fractions, we can go a little bit farther and say that's 3 over 10 squared. Expand out the 10 squared, so now we've got 3 over 10 squared, which is 100. And now we see 3 over 100, that's something you're probably familiar with as 0.03. Or maybe even you know it as 3%. What if it was 30 times 10 to the -2nd? Let's see what happens there. So 30 times 10 to the -2nd, we're saying that's the same as 30 times 1 over 10 squared, which we've also said then is 30 over 100. And you know that you can cancel out the 2 zeros, so you end up with 3 over 10, which you probably remember as 0.3 or 30%. In scientific notation, a number is represented as a single-digit number followed by as many decimal places as you need to show all the digits, and then it's multiplied by whatever power of 10 is needed to not change the value of the number. For example, 42,756 would be written as 4.2756 times 10 to the 4th. We get there by saying we start with 42756. Now, we want to get it in scientific notation, which means we're going to have a decimal right after the 4. So we put the rest of the numbers. So we got that decimal in the place right after the first digit. Now we have to ask ourselves, what number are we going to put on the times 10? So what exponent do we have on the 10? We figure that out by looking at where did we move the decimal place. This is kind of the opposite of what we were doing when we were multiplying. This time, we're saying the decimal place started there, and it moved 1, 2, 3, 4 positions. Since it moved 4 positions to the left this time, that's basically the same as dividing this number, 42,756. We have effectively divided it by 10,000. So if we're dividing by 10,000, that is 10 to the 4th. So if we've divided this number by 10 to the 4th, that means we have to multiply this number by that same number. The decimal 0.00472 would be written as 4.72 times 10 to the -3rd, or 0.001. The 4 needs to be in the thousands place, not the ones place. So you divide 4.72 by 1,000, or you multiply by 1,000, which is 10 to the -3rd. Using the process that we used in the last example, if we've got 0.00472, we want to end up with 4.72 times 10 to some exponent, we don't know yet. And this time, though, we're moving the decimal to the right, 1, 2, 3 positions. So since we've multiplied this number by 1,000, by 10 to the 3rd, we have to then divide this number by that same value. So we do that division by putting it as a 10 to the minus third. So if you're making the number over here something bigger, as we did in this case, it went from a small decimal to being the number 4, that means we're moving the decimal place to the right. We're multiplying, so we're making it bigger, which means we have to do a negative exponent to make that smaller. It's easier to compare a group of very large or very small numbers if they're written in scientific notation, since you can often focus just on the power of 10 to help you quickly decide which number is greater and which is less. In this example, you can see we've got a 10 to the third, a 10 to the second, and a 10 to the minus first. It's very easy to see then that the number with 10 to the minus first is going to be the smallest number, and the 10 to the third is going to be the largest number. Even though your first reaction might have been to say, oh, there's a 9.4 here, that's clearly bigger than 5 and clearly bigger than 3. But because they're being multiplied by different size factors of 10, that affects the overall size of the number. Of course, just as with standard form, if the power of 10 is the same, you have to look at the values of the digits. So you see in this case, we've got 10 to the third in both cases, so we have to then pay attention. This one's 3.9 and this one's 3.7, so clearly the 3.986 times 10 to the third is the larger number. There are a lot of ways to write numbers as powers of 10 other than scientific notation. For example, you could write 42,517.358 in any of the following ways. You can see the only difference is the position of the decimal in each one shifts, and as a consequence, the size of the exponent also changes. Typically, we're going to work in scientific notation because that's usually the easiest number to work with. However, sometimes you may change to something that is more comfortable units. So the 10 cubed, supposing we had been told that this number represented something in meters. So we've got 42,517 meters of road that we've traveled. That's a fairly difficult number to kind of get our head around and understand. But if we change it into the format of 42.517 times 10 to the third, 10 to the third helps us out because we recognize, well, hopefully you recognize from previous grades, that 10 to the third is the kilo prefix in metric. So 42,517.358 meters would be 42.517358 kilometers, which you would probably just round off to say 42.5 kilometers. Key terms. Power of 10. Power of 10 is a number that's written as 10 to the n. For example, 10 to the first, or 10 to the second, or 10 to the third, and so on. Scientific notation. Scientific notation is a form of a number written as a single digit, possibly followed by decimal values, that's multiplied by a power of 10. For example, 3.1 times 10 to the fifth. Standard form. Standard form is the usual form of a number, that is, the numeral, for example, 3, 4, 5, 6. Your turn.